I welcome you all for my presentation. The paper titled Investigation of Harmonics in a Transient Over Voltage due to Capacitor Switching on Distribution Network. The contents of the today presentation, it is covered starting from introduction, then objective of the paper, under capacitor switching basic concept and simulating model and the simulation results and the experimental setup and results and conclusion and references. And in the introduction side, okay, the power quality is a topic for constant study in power systems, and generally the power quality it depends upon the power electronics component and nonlinear load appear in the any network. It is the major component one create the power quality problem in the power network. However, the harmonic distortion from source can be magnified by the application of power factor correction capacitor. Okay, now the most of the industrial distribution system or transmission system, they are using power factor correction capacitor to improve the power factor. So this is also one of the major source to induce the harmonics in the power system. So for years, capacitor have been used for power factor correction, and another one is for voltage regulation also. So, however, the use of this capacitor may create parallel or series resonance problems, increasing the harmonic distortion of the voltage and current waveform. Okay, and then switching of the power factor correction capacitor. So they are using a shunt and a series type of capacitor, and they make switching when the power factor is going down. Okay, they want to improve the power factor of the given power network. So for this time, what happened during the switching? The transient over voltages produced contain high frequency components. So the transient over voltages induced in the system when the capacitors are switched for power factor improvement. So these transient over voltages, if it is large enough, okay, then can damage the sensitive equipment like protective equipment or power electronics converters used in the network in the power systems are damaged. So this is the major issue of the power network when we are using the power factor correction capacitor. So what is the objective of this paper? This paper addresses the transient over voltage and the harmonics induced by capacitor banging switching in the power system. And what is capacitor switching and energizing? Okay, the figure 1, it is a single circuit, and explain us how the capacitance switching and energizing is happen in the system. So we have the circuit diagram in single AC voltage sources and with the inductor series and switch and capacitor series. So we have to classify two cases, case 1 and case 2. In the case 1, so what happened at this instant, a capacitor bang is connected with the source. So what happened? The capacitor is a sudden short circuit because the voltage across the capacitor cannot change suddenly. This is a basic concept. Therefore, it will dip severely. This dip in voltage and the step change in the transient is a function of source impedance. Source impedance behind the bus. So later on, the voltage will then recover through the high frequency oscillation. So what happened? In the initial condition, overshoot of the voltage has theoretical peak value 2 times of the maximum value of crest voltage. So which can recover about half of the cycle. So half of the cycle, it will reach the peak voltage 2 times of the crest voltage. This is for case 1 and when the capacitor is connected with the source. What about the case 2? The case 2, when capacitor is switched off, the same effect is observed if restrike occurs during the switching operation. So this is for case 2. This is the basic concept they are using for capacitance switching and energizing the power system. Study model we develop by using MATLAB, Simulink, and we are selecting 11 kilowatt bus and 30 MVA capacity source feeder, and we are using RL load, this is a nonlinear load, and we have classified two buses. One is for 11 kV bus, another one is for 0.4 kV bus, and we can give the name is high. This is high voltage side, this is the low voltage side, and each bus we connected capacitor through the circuit breaker CP. So the transformer is connected for step down the voltages. And so this diagram is a single line diagram we have developed in Simulink, the model of this similar diagram. Also, if you see, this is the, we measure the uh, near the capacitor bank. This voltage and current values are near the capacitor bank. The figure 4, it is different than the figure 3. We are measuring the all the voltages and current for one phase close to the load, near the load side. So this variation you can see here, and this the close to the load, the another one is close to the capacitor bank. Okay, here also you can see the voltages are rise close to the 520 around, and this variations we can get for the different places we measure the voltage and the current. And next one, we focus very clearly for a transient voltage at one phase. A three-phase waveform we can see here, and we can see here the switching time. We select two different switching times. Okay, one is for 23 millisecond, another one is we increase the switching time. So that is 30 millisecond, but it is 0.4 kV bus. It is for improve the power factor purpose. Okay, in see the diagram figure 5 and figure 6, we have the peak voltage, we get it. But the summary of this one we tabulated, and the capacitor bank size we are using 40 kVR in the 0.4 kV buses, and the switching time we are using 23 millisecond and 30 millisecond in the table. You can see the result, and you see t equal 23 millisecond, we get the 548.6 volt, the peak voltage we get. And when t equal 30 millisecond, we get 544.5 volt. So it is less than the previous one. So what is the conclusion of this one study? Actually, when we increase the switching time, and we have very less peak voltages. When we increase the switching time in opposite way, we get the more peak voltages. So it's very important when you make a shunt capacitor switching for power factor improvement, you have to take care about the switching time. So if you fix the switching time in proper value as per the standard value, then you get the peak voltage within level. It is not harm or damage the sensitive productive equipment in the power system. So this is our conclusion from this research. And not only we concentrate the transient over voltages, and because of the switching, capacitance switching, okay, we observe the harmonics problem also. So we see here, we get the result of harmonics, total harmonic distortion DHT, voltage harmonics and current harmonics both we measure, and different switching times. Figure 7, voltage harmonics, 40 kVR capacitor when we are using, and at t equal 23 millisecond. When you see here, the result is 0.21% THT. So it is the under the standard of IEEE standard is less than 5%. And when we go for THT for figure 8 current harmonics, the same switching time and the same capacitor bank, we get the 0.27%. This is also under the IEEE standard less than 5%, 0.27% we get it. And when we go to the figure 9, it is the THT for voltage harmonics at switching time is we reduced now 19 millisecond. So what happened? But capacitor bank is same size 40 kVR. So what happened now? We see little increase in the THT value. This is 3.90% we get for the voltage harmonics. So this effect because of we reduce the switching time. And final the figure 8, it is THT for current harmonics. The time is same 19 millisecond switching time, but we are getting more than the standard value, that is 17.06% THT at this time of switching 19 millisecond of the current harmonics. So what is the summary? What is the conclusion? In the table 2 shows that it's we select two switching time 23 and 19, and we measure voltage harmonics and current harmonics, and we get when we get switching 23 millisecond, the harmonics levels are okay, voltage and current it is under the 5%. But when we switching at 19 millisecond, my voltage harmonics is okay as under the 5%, 3.90%, but my current harmonics is exceeding the standard value. So we have to very careful when we switch the capacitor with very frequently, very fast or very quickly. So that is the conclusion we can get from this result. And we do the experimental part in our labs, and with less capacity of the component. So if you see the left side, the diagram is this is our setup, experimental setup. We have the capacitors and all the values are given in the paper, and single phase transformer we are using PQ meter fluke company, and power meters we are using, an inductor load for non-linear RL load we are using, and we get the result. We measure by using fluke meter. We get the figure A in the right side, B and C and D for different order of the harmonics, 5th order, 7th order, 11th order and 13th order of harmonics, and the corresponding THT, and how much value of the 5th harmonics and everything we get from the fluke meter. And this is for low level capacity of the component we use, and we confirm that in our study in the previous one, and this one it's in right way is going. Okay, so when you summary of this experimental result, we measure all the odd harmonics, 5th, 7th, 11th, and 13th order of the harmonics. We make it only one time of switching, and we get the voltage harmonics and current DHT values also we get. So when you see here, when 5th harmonics, 5th order, and this is under 5%, is acceptable as per the IEEE standard. And when you go to the 7th order, it is clearly mentioned voltage DHT is okay. It is under the 5%, but current DHT value is exceeding the standard value. It is 18.4. It is the we have to consider this one. And 11th harmonics also, the voltage is okay, 0.4, but when go for current is slightly exceed the 5%, is 5.5. But when you go to the higher order harmonic, 13 order, so we get the under the standard value, that is 0.3 and 4.5. So what is the conclusion of this one? And the 7th order harmonics is the one is exceeding the standard IEEE standard value, that is 18.4 in the current harmonic side. Even voltage harmonics is under 5%. So this is we observe from our laboratory part, and we make we develop the small scale prototype model, and we get different order of the THD value. So how we control the switching transient, okay, in the large scale system. So how we mitigation of control of switching transient revolve around the following. So we can do the minimizing number of and severity of switching. So we have to see minimize the number of switching time of the capacitor, and minimizing number of times, and severity of the switching events, and limitation of rate of exchange of energy that prevails among the system element during the transient period. This is also another way we can control, and shifting the resonance point to avoid amplification of the particular offensive frequencies. So this is also one of the point to avoid the transient over voltages and harmonics problem in the power network. And the next one is the provision of energy reservoirs, okay, for storage to contain released trapped energy within the safe limit of current support for to avoid transient over voltage. The last one, the provision of discharge path for high frequency current resulting from the switching. So these are all the mitigation measure we consider or we taken in the real system, in the large scale system. We can avoid transient over voltage and harmonic issues during the switching of the capacitor for improve the power factors. The conclusion, the purpose of the study is study the transients from the utility capacitor bank switching of the realization of the real system, and we studied harmonics and transient over voltages for the different switching time and different places close to the load and close to the capacitor buses, low level buses. And in addition that, we did a small scale model in our laboratory test system. We observed different order of the harmonics, and 7th order harmonics is a little bit high than the standard, so that we have to take care when we design the power network. So this is our paper. Thank you very much. These are our references we are using. Thank you very much for your time, and thank you.